I want to just to present a slide about with the title, The Collapse in the Head, which wants to approach the main content of this workshop. So what happens? What is the is there a possible relation between collapsing mind, collapsing consciousness? Of course, the Penrose and collaborators suggested something along this line. This is a very difficult question. I will not enter into in detail in this question, because consciousness itself is a delicate subject. So if you want to put even the collapse on top of that, it will become even more complicated. I want just to say something that has been discussed theoretically so far. And in particular, what happens to the perceptive process in the human eye. It could be so smell or whatever, something in the ear, whatever. So the visual process is more, at least psychologically, more effective. So suppose that you send to the eye a superposition of a photon going to the, for example, to the left eye, or a limited number. Photon is not sufficient probably, but a very limited number of photons, 5, 6, I think that's the threshold of vision, about 10 or less photons, that you send in a superposition of going to the left eye or to the right eye of a person. Now, the question is, so this is a microscopic superposition. It's even superposition of photons. Photons are basically not affected by collapse models. They remain in superposition for as long as you want. So what happens to this superposition when it hits the eye, the retina, and then it generates the electric signal which goes into the brain? So again, this is a very difficult question, because the visual process from the microscopic point of view, it's a very complicated system. The motion of all the ions and molecules, it's not easy to trigger. It's a stochastic process even, it's not deterministic, of course, but you can say something, and some work has been done, and here you have some references over there. And basically, it's a very fascinating problem for the mathematical point of view, because you have the formation, so the formation of the progressive formation of a macroscopic superposition. And I mean with that, typically in a measurement process, you have micro and macro. The micro system in the superposition triggers the superposition of the macroscopic object, and then something happens to the object. Here instead, you have the progressive generation of the macroscopic superpositions. Over time, more and more atoms are included into the superposition during the perceptive process and during the building of the electric signal that goes into the brain. So on the one side, you have this micro to macro generation of a superposition. On top of that, you have the collapse of the wave function. So which of the two wins? How does it go over time? So again, this is a difficult question if you want to really study what happens in the eye. And so what has been done simply is to, so far, is to see at which point the number of particles or ions, let's say, that are included in the superposition is large enough in order to sharply kill the superposition. And then the answer, so basically, at which stage of the perceptive process does the collapse become strong enough? And then depends on the value of the collapse parameter. If you remember, there is lambda and RC in the CSL model. This has been studied for the CSL model. And in particular, suppose that we fix RC. So the question is, how does the collapse during the visual process depend on lambda? And basically, there are two possibilities. If you take a strong value for lambda, we'll tell you later about these numerical values, suggested by Adler, then you can see that the collapse of the wave function becomes effective when the the photons hit the retina and start triggering the visual process. So basically where you have seen something, not in the brain, but in the eye. The eye reacts to the visual process. So at that stage, you already have a large enough number of ions included into the chemical process and into the superposition chemical process in the left eye plus chemical process in the right eye, that everything collapses and you have a classical signal, a classical outcome, which is brought to the brain through the optical nerve, and that's a classical signal with the classical visual perception and then the classical reaction of the brain to that perception. I've seen something with the right eye, with the left eye, or I've seen something with the right eye. instead, if you take the GRW value which is a weaker value, some 8, 9 orders of magnitude weaker value for the collapse strength, then the quantum to classical transition doesn't occur in the eye. It occurs much later. So the reaction of the eye is still quantum, superposition of a chemical reaction in the left and superposition of the chemical reaction in the right. Then you have the electric signal that goes through the optical nerve to the brain, and you have a superposition of a signal generated in one optical nerve and the signal generated in the other optical nerve. And basically, when you are more or less at the end, when the optical nerve merges with the brain, that you have a classical, the quantum classical transition. So at the end, I mean, for the typical values of collapse models, you can guarantee that you have a classical perception and then a classical reaction of the brain. And that's why basically we see a classical world that we behave like classical people. So this is not really the answer to the emergence of consciousness or whatever, but it's something, a more physical question, a much easier question to answer when a quantum signal becomes a classical signal. The question, the more detailed question of analyzing this problem dynamically, so to take the collapse and the formation of the superposition really together as a dynamical, as two competing processes within the same dynamics, is still an open question. Actually, it's part of an FQI project that we also that we won, which is, I think, at the same time where the project, which is the trigger of this workshop, has been granted. Okay, so this is what I can say about the collapse and the visual process, the collapse in the head. Okay, so why should the wave function collapse? That's also an interesting question. Collapse models do not tell why, they tell how, but not why. And why is another difficult question. There is no unique answer, not clear answer. According to GRW, the original proponents of collapse models, this is, and also Philip Pearl, I would say, the answer was, I think, is it's nature. Nature is such that the fundamental equations are nonlinear and stochastic. They're not linear. They are nonlinear. So it's a property of nature. But I think that still the origin of the question of why the wave function collapses calls for a physical answer. And one answer has been given by Penrose, and who relates the collapse of the wave function to gravity. And his argument, more or less, is the following one. When you have a superposition space, we're talking always of a matter superposition, of massive superposition space. If you inject into this description a little bit of quantum gravity, then the superposition in space of mass in space generates a superposition of two different space-times. A bump here, if the mass is located here, and plus a bump there in space-time where the other component of the superposition is located. And then he says that the correct quantum theory of gravity should not allow for such superpositions of space-time. So the problem is not with the superposition of matter. The problem is for him is with the superposition of different space-time. For him, this is not a stable state of a quantum theory of gravity. It is a state that should localize over time. And then he gives some mathematical arguments as to why he thinks this is the case. And then if the superposition of space-time collapses into one of the two possibilities, then it brings also matter. The collapse of the system with it. So the space-time collapses, and also the matter field collapses and becomes localized in space. So this is the general idea. Of course, making a theory out of this would be the holy grail of most people. It's a very difficult question, but Penrose was succeeding in giving an estimate of the times, at least of the time scale at which the collapse should occur. And the estimate is in this picture made by Penrose himself. So the time, the lifetime of a massive superposition should be given by h bar over some energy. So this is the usual Heisenberg relation. So where the energy is computed as the gravitational content of the superposition. So in the normal, I mean, it could be in the general relativistic setting, but it's much more easier to compute in the Newtonian. So you can well imagine that if you have a proton here plus a proton there, the gravitational content is very weak, and so nothing happens. But if you have the Schrödinger cat here plus the Schrödinger cat there, the gravitational content is much larger, and something could happen. And actually, if you plug in the numbers, you can see that the lifetime of the superposition of a proton is very large, and the lifetime of the superposition of the Schrödinger cat is very short. So again, a quantum to classical transition. Sorry, but okay. Now I want to come to the testability of these models. These models are experimentally testable because the Schrödinger equation is modified. It's modified by adding additional terms, additional effects that you can try to test these effects. And there are two strategies which can be employed: interferometric and non-interferometric experiments. So interferometric experiments is basically the double slit experiment, as I showed in the picture. So the idea is that you take a system which is as large as possible, as massive as possible. You create a superposition. You keep the superposition for as long as possible in a protected environment, so no decoherence, and then you do the double slit experiment. If you see an interference pattern, that means that the superposition lived for all the time, and then collapse models are wrong because collapse models predicted that the superposition should not survive. Or if you see that, or if you do not see an interference pattern, then something happened. And the question is, what happened there? Then we have to investigate whether collapse models are right, or something went wrong with the experiment, or there was an unknown degree of freedom which was not taken into account, whatever, something happened. The other possibility is to perform non-interferometric experiments. Non-interferometric experiments are based, basically, I hope that the picture conveys the message. Are based on the indirect effect of the collapse mechanism. That every time you collapse the wave function, you also move the center of mass. So if there is a collapse mechanism, there is also a diffusion process. So the picture gives an idea, but one should look at the equation in the end. So if you take a superposition, the center of mass is located in the middle, so the mean position. But if you collapse to one of the two possibilities, the center of mass moves to the left or to the right in the picture. So the collapse, so this is just a pictorial way of representing a mathematical fact that a collapse dynamics induces a diffusion of the particle. According to standard quantum mechanics, the particle should go straight if there is no other force, of course. According to collapse models, it will jiggle because there is this noise, the collapse noise that disturbs the dynamics, which is omnipresent. It's always there. You cannot isolate it. So what are the advantages or disadvantages of the two approaches? The advantages of interferometric experiments is that they are a direct test of the superposition principles. You can even forget about collapse models. You are testing whether superpositions are there or not. So this is very important. But there is also a minus side. They are very difficult to perform. So it's very difficult to take a large system, keep it isolated, prepare a superposition, maintain the superposition, and detect the superposition. It's extremely difficult to do that. And in fact, at the moment, the world record for a delocalized state was achieved with some molecules weighing 10 to the 5 atomic mass unit. So a molecule with 10 to the 5, 10,000 nucleons. So about, roughly speaking, 1,000 atoms, which was a success from the experimental point of view. It's very difficult to perform such experiments, but it's still, you're not probing the macroscopic domain. You're still in the low mesoscopic world. Or the largest delocalization, about half a meter, was achieved in a lab, but with single atoms. So it's a macroscopic delocalization, but for a microscopic system. So non-interferometric experiments instead are the opposite. So the minus side is that they are not a direct test of the superposition principle. They are a direct test of collapse models. They are, but not of the superposition principle per se. And but they are much easier to perform. So